problem states that we have 400 feet of fencing and we want to construct a rectangular pen for cattle. What are the dimensions for the pen? Then maximize the area, okay? So with these optimization problems, it's always really helpful to try to break it down in plain English and understand what it's asking. So the question or our answer is going to be dimensions, right? We want dimensions of what? Of a pen. Of what pen? A rectangular pen in specific. And then we want to maximize that area. How do we maximize that area? What do we have to work with? We have 400 feet of fencing to work with. 400 feet of fencing is our perimeter, okay? So let's draw a visual, because these are always very helpful. Okay, here's our rectangular pen, and then here's we have 400 feet of fencing to work with. Okay, this is our given. So we have some perimeter it's gonna add up to 400 feet, and we want to maximize this area, right? We want to have, the application of this problem is how can we make this rectangular pen maximize the area with 400 feet, right? We don't want a pen that has an area like that and that's, using all the fence. We want to try to figure out how we can get the most symmetrical max area for this rectangular pen, okay? So the area of a rectangle is just the length times its width, right? The area of a rectangle is just its length times the width. Or instead of labeling this W and L, we could just say X and Y. Well, we could also say that this is also Y, right? Because these sides are equal. These sides are parallel, I should say. These sides are parallel, so they're of equal length. And so we could also say that this is X right here. So we could also say the area is just X times Y, right? Now let's set up an equation that will help us solve the area, right? Figure out this area. So let's change colors and let's write perimeter right here. Perimeter. And we want to write an equation that correlates the perimeter somehow into this. So what we could say is, okay, well, we have 2x's, and we have 2y's. 2x plus 2y is going to equal our perimeter, 400. So we can conclude that, right? Okay, 2x plus 2y, we don't know what x or y are, but it's going to equal 400 because 400 is our perimeter. Well, we could actually solve for a variable in this case. We could solve for an x or a y. I'm going to solve for the x in this case, and that's going to give us 2x. If we subtract 2y from both sides, right, we're going to get 2x equals 400 minus 2y. And then we could isolate the 2x, or isolate the x by dividing by 2. So we'd have x equals 200 divided by, 200 minus y. Because 400 divided by 2 is 200, and negative 2 divided by 2 is just negative 1, or negative y. So we have an x right here. What can we do with this? What can we do with this x? Well, we could plug it in to our area formula, okay? So let's do that. Let's plug this x into our area formula. So we could rewrite right here, the area equals x times y, or we'll just say y times x, y times our x, which is 200 minus y. And then we could distribute. We'll get 200y minus y squared. Now, there's something you can note at this particular point, right? Because remember, we're trying to find the maximum of this rectangular pen. We want to maximize the area. Well, this is sort of a little hint, or a way that you can tell that you're getting the maximum of something. You see this negative y squared right here? Well, that means that this is a parabola, but it's not just any parabola, right? It's not just it's not just I guess when we think of a parabola, we probably just think of one typically like that. But this, with the negative sign, that's going to make this parabola an upside down parabola. And what is this area called? That's called a maximum. So how do we get that maximum? We take the first derivative of this and we set it equal to 0. So let's do that. Let's take the first derivative of this, which is going to be 200, and this is going to be 2y, and let's set it equal to 0. And let's add the 2y to both sides, 2y, and we get that y equals 100. We get that y equals 100. So we have our y. We have our y, 100, 100. Now, obviously, you can presume that the x's are both going to be hundreds as well, but let's just plug it into here, right? If we plug the 100 right here, well, yeah, we're going to get the x equals 100. So what are our dimensions going to be? They're going to be 100 feet by 100 feet. That's how we get the dimensions that maximize the area of this rectangular pen. So to just recap really quick on what we did, we drew a picture, we set up our x's and y's, we knew that we had 400 feet to work with, we set up an equation so we could isolate the x, and then what we did was we were able to plug the x into our area formula, and then we were able to realize, okay, we're gonna have a maximum. How do we find that maximum, right? Well, we find it by setting the first derivative equal to 0. We get our y equals 100, and then we get the x equals 100, and then we get our dimensions at 100 feet by 100 feet. I hope that made sense, and that's how you do this optimization problem. Thanks.